This is January 27th. Good afternoon. This is CS797K, Perspectives on Data Science. For today's lecture, we're going to go through Python and just do a quick overview of the tool we're going to use and go through Python. How many people are in CS746 as well? Okay, and are you in the Monday? Were you in the section we just did? This could be boring as heck. Just, so if you were already in the 746 class, yeah, you can go over and tell Ajay and Harika, I can't stand it. I'm too bored. I'm leaving. And they can check you in and give you attendance. Anyhow, but I'll try to be slightly, I could just do the slides from last semester and then it'll be different at least. No, the slides from this semester are better. Okay, Python, Jupyter, toolbar. We're going to use Jupyter in here. You're going to go out to Anaconda. And you're going to download, sorry? Yes, go over and talk to these two over here. If you are in the 746 lecture, go tell them I was in 746. Please count me as, oh, you know what we can do? We can just do our attendance right now, right? Yeah, okay, here we'll do it this way. I'm sorry. Attendance, here you go. Okay, yeah. So if you were already in 746 and don't want to stick around for the same lecture twice in a row, you can take off. But go check in and let them know you're here so you get your attendance credit for today. All right. If you already know Python and decide you're bored in the middle of the lecture, do that too. I'm just going to go ahead and start. So Jupyter is the tool we're going to use in here. We can start Jupyter. On this laptop, because we've already installed it, we just go down here, we type in Jupyter Notebook. It will pop up a console window and start the interactive session in the web browser. In the web browser, it will come up looking like this tab here, Jupyter logo. It will show me the hard drive contents. I can go out here to the downloads where I've already downloaded the sample program we're going to use. So for instance, we want to do some illustrations of strings, tuples, lists, methods. So we can just run this code here with this cell here, and it will go ahead and print out the text. If I go to do this, kernel, restart and clear everything, you see a clean, empty program is listed here. It's got markdown cells that is just documentation, and it's got code cells, which are executable code. So here's my C programming. I'll go ahead and run this. It will go ahead and print out these output there. And so I can just keep on going through here and run everything. It'll be pretty quick and sturdy here. So lists and tuples and dictionaries, and we get all of our output there. So now we're going to go back to the slides. The title bar, the toolbar up there has save, create new cells, copy, paste things, move cells up and down, run the code, stop, reset, clear execution, change the type of the block. So if you want to take code and you don't want it to actually run, you can just change that to markdown. It might look a little weird, but it won't execute when you try to run your Jupyter code. You can also use Google Colab if you're in a team, project team. You can go ahead and Google Colab stands for collaboratory. It's integration of Jupyter Notebook with Google Drive. It's helpful for working in teams. And there's a URL to find Google Colab and download that if you want to do that for your team. You don't have to, but you might find it useful. Python was originally invented in 1991 or written in 1991 by Guido van Rossum. He's the benevolent Python dictator for life, except he retired. So anyhow, he created it as an open source programming language. So didn't try to charge money for it, basically released it for anybody to use, asked the software developer community out there to help them make the language better. And a lot of people fairly quickly decided that Python was a wonderful language, mostly because it's clean. Many other languages had the idea that if you wanted to have a loop statement and the things were inside the loop, you had to put curly braces or something around it to say this is what's inside the loop, and the compiler would look at these characters to tell. Guido decided he was going to make white space. So if you have a for loop, then everything inside that for loop is indented the same amount is considered to be a part of the for loop. And when you end that indentation, the for loop ends. It looks like the code runs. When I saw that, I was really skeptical. I thought, why is he doing that? Because I'm old enough to remember when Python was, yes, I'm ancient. Stop rubbing it in. Anyhow, but that white space turns out to be an incredibly powerful concept, because when a person looks at that code, this is what they think in their head it's going to look like and do. And if you don't put your curly braces in there, your code doesn't do what you want it to, right? Very clean language. High level interpreted, meaning it abstracts all the hardware dependencies away. There's all sorts of things you can do down in the hardware and the central processing unit of different computers. There's lots of different command sets and everything like that. Anybody, if you ever studied assembly language, how many people have studied assembly language? One person. Hardcore. Two people. Okay. Assembly language is right down there, working bare metal kind of stuff, right? You're actually down there telling the CPU execute this command, so on and so forth, right? Sorry? Well, Linux is command line. Command line is below GUI. GUI, graphical user interface, fancy stuff. Command line is doing things. The command line interface for Linux is very similar to the command line interface for Macintosh, because the Macintosh is based on BSD, which is a variant of Unix, just like Linux is a variant of Unix. No, I'm talking about down in the hardware, the chip that runs the computer, right? It has its own language that it understands. And the chips that are in Apple phones is different from the chips that are in the Apple computers, is different from the chips that are in Windows computers, different from the chips that are in older computers. When I was a kid, we had this giant computer in this basement room that filled up the room and had a 36-bit instruction word. No one uses that. It was just massive and ancient. And today we'd look at it and say, man, that's pathetically weak compared to my phone, right? So anyhow, high level means that you don't have to worry about what kind of hardware you're running on. Low level means you have to write your code specifically for that operating system, specifically for that piece of hardware, right? It's interpreted. That means evaluate on the fly. In other words, you write your Python code, you can execute straight out of that .py file, .ipynb file, whatever it is. Some programming languages like C is the classic example. Fortran are compiled languages where you start with a text, you run it through this step where it takes that and it converts it into executable code. It actually converts it into machine language, and then it runs that machine language for you, right? And you can't read the machine language. If you want to debug it, you have to have a special purpose debugger, so on and so forth. Technically, Python is hybrid compiled interpreted. You're actually running it one line at a time, but it actually kind of creates what's called the Python bytecode, which is kind of a shorthand version of the code you just wrote. And then it actually is running that shorthand version, and then it's presenting errors back to your screen. So it's actually internally a little more efficient. Rearranges things a little bit to make your code run better. We'll see that later when we talk about lists versus tuples, why or how it does that efficiency. It's useful for scripting system maintenance. If you have a Mac computer, a lot of the system code in your Mac's computer, Apple computer, is written in Python. Every MacBook comes with Python included, right? And that's why you got to be careful installing Python on a MacBook, because you don't want to step on the system Python, because Python is a programming language. It's a tool like every other tool. It changes with time. So there's old Python that is actually incompatible with new Python. If you read about Python 2, it was a very different language than Python 3 that's out there now, right? There's a huge set of libraries. Why is it called Python? Is Is Guido von Rossum a big snake fan? No. He's a fan of an old comedy program on BBC called Monty Python's Flying Circus. If you haven't seen Monty Python and the Holy Grail, it's a very silly movie, and you should go watch it. Anyhow, if you click on this link, I'm not going to do it here because it takes too long to load it, but it's the intro for Monty Python's Flying Circus and the silly song that they play and so on. Different ways to run Python. You can actually create a file, you store it on your computer just like a Word document, and then you just say Python in that file, and if everything's loaded and configured correctly, it'll run that program. Or you can not even say Python. If you create, like on Windows, you create a batch file, or if you go on a Linux box and you put a shebang line at the top that says this is a Python program, you just type in that file name and it'll run. Right? You can use the Python console, also called the idle loop after actor Eric Idle, who was a member of Monty Python's Flying Circus. Right? Just type in statements, or you can use any some sort of integrated development environment. Jupyter, Spider, PyCharm, Microsoft's Visual Studio Code, Google's Colab, so on and so forth, right? Lots of different development environments for Python out there. Bugs. I have a small program. Why are bugs called bugs? Because the first bug was a bug. And here it is. This is the notebook from, I think, 1950, middle 1950s, something like that. And Grace Hopper, Admiral Grace Hopper, was running this National Naval Observatory computer. They had this massive mechanical computer, and it ran on relays. It had physical switches that would turn on and off to indicate ones and zeros. And the thing stopped working. It wouldn't run the program, and they sent the technician in crawling inside the computer because, you know, the computer was as big as a house, right? And they found relay number 70, panel F. There, the relay wasn't working because there was a bug that had crawled in, got squished, and it couldn't make contact. So the very first computer bug was an actual bug. Yes, and so that's why we call removing bugs debugging. We're getting the bugs out of our code. There are three types of bugs. There's a syntax error, where you type in something that's completely wrong and it'll never run, right? If you try to type C code into a Python interpreter, it won't run, right? So again, if I say print hello world, that is a syntax error. Can you see the syntax error on that line? Is the text big enough? There is print, no semicolons in Python. You don't need semicolons. It's the fact that there's double quote in the front and a single quote on the back. The string has to be terminated with, you know, the same delimiter on the beginning and the end, right? Not only that, this first quote is not actually a double quote mark. That is a Windows PowerPoint trying to be fancy and giving me an actual opening quote, open double quote, and a closed double quote. And there's actually a special character in ASCII that's a standard double quote. It doesn't have a beginning and an end, and it would just go straight up and down. And we'll see that in some of the later things, but that is actually two syntax errors in one, two for the price of one. Runtime errors, exceptions, an error that occurs during running the program. If I say A equals 5 and B equals 0, say print A over B, I'm trying to divide by 0. You cannot do that. Your program will have to crash, right? Unless you do something to handle it. Semantic errors is when you've written code and it looks fine, it works great, but it doesn't do what you intended it to. If I say the sum of A and B is A minus B, right? It's going to tell me that 5 plus 2 is 3, which obviously is wrong, right? But you know, some of the worst bugs are those subtle semantic errors where you've made some mistake. You know, you've actually got two variables with real similar names and you brought the wrong one in or something like that. Here's examples of it. Zero division error, that's the error message we get. Zero division error, division by 0. Here's trying to add a string and an integer together, type error, right? You can't mix these two types. They don't work together. I can say, I could switch this around. Nope. I could say string times 10. I could multiply a string by an integer, which gives me that string multiple times, right? But I can't add an integer to a string. Index error, if I have a list of elements and there's only 5 elements in there, 1, 2, 3, 4, 5. The first element is at position 0. The second one is position 1, 2, 3. The last one is at position 4. So there is no list sub 5. It'll say list index out of range. And you'll look at that and you'll go, wait a minute, what? Why is this right? Because you're not remembering that in computer science, everything starts at 0, right? So a 5-element array is numbers 0 through 4. A key error, if you have a dictionary, which is accessed by keys, like A and B, and those are correct quotes. They just go straight up and down. They don't slant one way or the other, right? If I try to print out my dictionary sub C, it doesn't exist. I'll get a key error. If I try to use a non-existent attribute of an object, for instance, if I have a number and I try to append to it, append is something you can do to a list. You can add things on the end of the list, right? But you can't append to a number. You get an attribute error. I don't have that. I don't have a method named append to apply to this object. Import error. Import Thomas. No module named Thomas found. Module not found error. Thomas, of course, is a children's show from England. Thomas the Tank Engine not a Python library. How many people have seen Thomas the Tank Engine? 1, 2, no, okay. It was big a few years ago. It's not so great now. Anyhow, file not found error. You try to open a file and read it. The file doesn't exist. You'll get a file not found error. And of course, unless we do something to somehow catch these errors, right? This program is just going to stop. I can do other things. Overflow error. Math thought exponentiation to 1,000, right? And if I try to range it, I get a range error. If I try to say large list is 1, and then I'm just going to have 1, 1, 1. Is the list is just full of ones? There's going to be 10 to the power of 10, right? So just a huge list of ones. And if I were to actually run that with a sufficiently large exponent in here, it would say I'm out of memory. And get a memory error. If I have a recursion error, define a recursive function. Recursive function is recursive because it calls itself. Fibonacci series, calculating that is the classic recursive function. I'm sure you studied that in your CS classes as an undergraduate. This has no end case. It's just going to go on infinite recursing until the interpreter says, that's it, you're done here, you've recursed too much. Here's some syntax errors. These are errors related to the structure of the program. So this is correct. Hello world? Correct. Hello world doesn't care how you spell your strings. You can spell your words wrong all you want to, right? But if you try to leave off the opening quote mark, not colon, but missing quote mark, then it'll say unterminated string literal. So I've left off the quote to open the string, right? A semantic error. Again, we've seen that already, 5 minus 3 instead of 5 plus 3, right? Unbound local error. If I define a function and I define a variable in there, say x equals 10, when I say that x equals 10, I've created x. I have now made that assignment to the variable. But if I try to print x, it doesn't have a value yet until after that x equals 10 line. So if I were to switch those two lines, everything would be fine. But if I do it here, and I call example function, I'll see cannot access local variable x where it is not associated with the value. Goodness, I did a lot better in the first class. I've got a tickle in my throat now. What is error handling? Error handling is a process of managing and responding to errors or exceptions that occur during the execution of a program. So we talked about, runtime errors. Well, how do you handle runtime errors? Well, it's simple. You just say try the code, and if it doesn't work, you say accept. And this is what you do if you get that error. So if I tried to run x equals 5 divided by 0, I'll get a 0 division error. So I say try this, except if I get this error, I will print out a message, cannot divide by 0, and continue the program. So my program doesn't have to die if I do a divide by 0, right? I worked at NetApp Corporation for many years. We were building storage subsystems. Those things had to work. Customers had to access their data. If something went wrong on the inside, we had to carefully make sure that we had the right workarounds in there to recover from whatever kind of internal weird error we had, get that data back to the customer when they asked for it, right? So we had a lot of try except blocks in there, only they were in C and C++, not Python, because Python's not fast enough, yeah, for real-time stuff. It's an interpreted language. So you use a try block to wrap the code, use an except block afterwards to tell how to handle specific exceptions. If you have multiple exceptions, right? So for instance, ask someone to enter a number, input, which is going to prompt, say, give me a number, enter a number and ask for the number. If they don't type in a number, if they type in, foobar or something like that, they'll get a value error. You can't divide 10 by a string. If they type in 0, you'll get a 0 division error. So you can have different error messages depending on what the different error is that you get. Finally, and else are the concluding bits of your try except block. So again, you try something. If you get an error, file not found error, can't read the file, we print out file not found. If we don't get an error, we print out, yep, we got that file, print out, we successfully read the file. And finally, that always executes regardless of whether an exception occurred or not. So we try to open the file. If we fail to open the file, we print an error, file not found, but we still continue and close it, right? So, maybe the file is null and we try to do a read, we don't get any data, right? So on. So those are the, try, except, else, finally. We'll see some of these clauses in other program flow statements, right? But first, we're going to look at keywords. There are reserved words in Python that have predefined meanings, right? Try and except and finally and else. We've seen those. Those are keywords that are defined to actually have meaning to the Python interpreter. Ideally, you don't overwrite those and try to make them mean something else. That's kind of bad form, right? So you'll get errors if you try to use a keyword. Here is a list of all the keywords in Python. There are 35 of them. There they are. The variables are the things where you store the data during your program, right? So we have a few rules about naming variables. You can only use letters, numbers, and underscores in your variable name. You cannot start with a number. You can start with an underscore. In fact, Python has a bunch of variables inside it that are underscore, underscore. They start with 2 underscores. It's called a dunder variable, right? Double under, right? And those are variables that are like internal. You're not supposed to mess around with those, right? So if someone is in there digging around in the Python core software, you can read that code. You can go look at it. It's open source. That means it's available for you to look at. It's not hidden behind a wall or anything like that, right? But the double underscore says don't mess with this, right? We'll see some of that later. Underscore, underscore, init, underscore, underscore is a classic example of that. Case sensitive. My var with a big V and my var with a little v are different variables. You should avoid using Python keywords, even if you have a case different, right? And some of them it won't let you do at all. And you should also avoid using popular function names that are included in modules. When you start importing things, you're going to import names with it, right? So, it's basically be aware of things that are dangerous to use. Some valid versus invalid. Current balance, current minus balance. What does this do? This subtracts balance from current, right? That's a subtraction symbol, not an underscore. Here we try to put a space in. That's not going to work. It just thinks I'm listing out 2 different variables. Here I say for account versus account for. I can't begin with a number again, right? Underscore 42, that's fine. You can have a variable named underscore 3, you know, whatever, right? But you can't just start with a 42. You could have, you know, 17 underscores and then a 42, and it's fine, right? Total underscore sum. You can be uppercase. Generally, uppercase is indicating this is a constant that you shouldn't change. That's a convention from Python 2. Now we have immutable variables in Python 3, so we don't have to do that, but it's still a better convention to do that, right? And of course, it doesn't have total underscore $UM sum, right? Some programming languages, the famous one was a programming language called Perl, used special characters, $signs, @signs, things like that to indicate the type of the variable. And it was famously said to look like line noise, like you just had, you know, like gibberish on your text. So Python wants to be a clean language, so it avoids that. Finally, you don't put any quotes or anything around it. If you put a quote around it, you're creating a string. Now, if you're accessing, say, a pandas data frame, you can use strings because pandas does that kind of index, right? But you're not actually using a variable name in that case, right? So, but you can also use a variable name. Variables in Python. Again, print for account. I get an invalid decimal literal. I can't assign that value to that number there. It says that's not right. I can say print lambda. Lambda is a keyword for an anonymous function. I can't print that out. Invalid syntax. In Python, we also have operators. Arithmetic for mathematics, comparison for mathematical comparisons, logical for Boolean operations, bitwise, which is also Boolean, but at a lower level, assignment operators, identity, membership, and special operators. Arithmetic operators, plus, minus, times, divide, modulus or percent sign. Integer division, which is basically you divide A by B, and instead of returning a floating point number, you'll return the largest integer that's less than the actual answer. So here 15 divided by 4 is 3.75, and here 15//4 is 3. So it won't round up, it'll just go to the next lower number. Here's a question for you, trivia. What happens if one of those numbers is negative? If I say negative 15 divided by 4, is it going to be -3 or -4? Go find out for yourself if you care. If you don't care, it's not something that comes up very often. But exponentiation, A**B, that's going to be 15 raised to the power 4. Right? Operators have a precedence. I had this morning that I'm really looking forward to Harika doing this lecture tomorrow because I want to hear Harika say Punkt vor Strich. Anyhow, precedence of operators follows the PEMDAS or BODMAS format. What does this stand for? Parentheses, exponentiations, multiplication, division, addition, subtraction, or brackets, orders, division, multiplication, addition, subtraction. And of course, these are all terrible mnemonics because people look at these and they think multiplication becomes before division in America, and they think division comes before multiplication in England. And the fact is those are the same operator, right? Multiplication, division are really the same thing, right? It's just you've inverted it, one of those numbers, to do the division. And subtraction is the same thing as addition. You know, it's just one of the numbers happens to be less than 0, right? Germany is much better. Punkt vor Strich, dots before stripes. So add and subtract 2 stripes. In German, when they want to do multiplication, when they're writing on paper, they just put a dot. When they want to do division, they do 2 dots, like ratio, 4:3, is 4 divided by 3, right? So dots before stripes, straightforward. Beware of unary operators. Minus is subtraction, but is also just a unary negation. So for instance, if I say x equals -4 plus 3, or x equals 4 plus -3, it'll bind that minus to the number before it does the addition. But it does that binding after it does exponentiation. So if in your program you have -4 raised to the power of 2, you're not going to get -4 times -4. You're going to get 4 times 4 and then negated. So this result here is -16. Maybe we should call it BODMAS, brackets, order, series, division, multiplication. Who knows? In any case, use parentheses. Avoid confusion. Liberally sprinkle your code with parentheses. Make it look like a Lisp program, and everybody will be happy. Lisp. Anybody know Lisp? Why that went? Never mind. Lisp was a programming language that was invented way back in the 1940s before there were computers to run it on. It was a list processing. It was developed by a mathematician. It has tons of parentheses. The joke is that it doesn't stand for list processing. It stands for lots of idiotic, stupid parentheses. Anyhow, you had to be there. Bad joke. Comparison operators. A is 10, B is 203. Are they equal? False. Are they not equal? True. Is A bigger than B? Nope. That's false. Is A less than B? So you see what we're doing is we're comparing two numeric operators. We're returning a Boolean result, true or false. Right? Logical operators is how we work with those Boolean values. Now, interestingly enough, Booleans and integers are closely related, where the integer 0 is false and any other integer is true. Right? So the closely related there. So if I say print A and B, well, only one of those is true, so the total of A and B is false. If I say print A or B, since A is true, that is true. If I say print not A, I'll get false. Straightforward, right? I also have what's called bitwise operators. These are doing binary or Boolean operations, but it's doing it a bitwise basis. We'll see that a lot in this class. Because that's what a RAID subsystem it is. It takes the data on one drive and it does bitwise XORing with all the other drives and gets what's called a parity out the back end. Parity allows you to reconstruct the data if a drive fails. Right? So important operation here, right here, the binary XOR. So we're going to take A equals 10 and B equals 4. You see there's no overlap between any of those bits, right? So what we're doing is we're basically doing a bunch of Boolean ORs, Boolean ANDs. 0 and 0, that's false. 1 and 0, 0 and 1, 1 and 0, those are all false. So the AND is a 0. The OR, 1 or 1, 0 is 1, 0 or 1, 1 or 0, so we get 1, 1, 1, 0. Binary XOR, if we had two 1s, XOR says, if they're different, then the result's true. Binary not, tilde A. I have to go try this out myself. This really works like this? Yeah? Because what it's doing is it's actually extending that value way out to a full 64-bit integer, flipping every single bit in that integer, right? And then that turns it into a negative number. And now all of a sudden you're looking at 2's complement notation. And 2's complement notation, weirdly enough, is 1 off of, so actually -10, the actual number would be 111100101. So we need to go tweak that one a little bit. Binary left and right shift, we can take our number and we just move the bits left and right. Those are our binary operators. And again, this is actually machine level code, right? Your computers are working with binary bits. And so we're actually down there dealing with the actual individual bits in there. We're seeing peculiarities of the machine here that are exposed. It's inevitable that you can't hide everything, right? There are 1's complement computers out there, which the negation is different. Whatever. Assignment operators, A plus equals 3. So instead of writing A equals A plus 3, which is too wordy, we're going to save ourselves like 3 entire keystrokes and say A plus equals 3, right? So because we're lazy, right? A minus equals 2, A times equals 4, A slash equals 6, right? So whatever A happens to be, we get our results out of there. Identity operators. These are not asking, are things equal? We already got that comparison operator, double equal sign, right? This is asking, are they the same? So this is a list of the values in the list are 1, 2, 3. You have to imagine that list lives someplace in the memory that as your computer is running. And the list has a name, and the name is A. And when I say B equals 1, 2, 3, this is another list. Just because the values in the list are the same doesn't mean they are the same thing, right? So A and B are two different entities. If I say print A is B, it will say false. Down here, I say C equals A. So when I say C equals A, I've said now this thing that is A has the name A. I'm going to give it another name. And that second name, the alias, is C. So C and A literally are the same thing. And you can't obviously be the same thing without being equal to each other, right? But you can be equal to each other without being the same actual entity. So, you know, when I was studying computer as an undergraduate, I ended up having to like imagine just, you know, things floating around in computer memory and just stuff, right? And I don't know if your imagination works that way or not, but that's what I had to do back in the day. A is not B, and that is true. A, if I say A is B, it's false. If I say not B, right, or not A is B, same thing, I'll get a true on that. Check if a value exists in a sequence. If I got a list of 4 values, is 2 in that sequence? Yes, it is. Is 5 in that sequence? No. 5 not in A. True. 5 in A is false. The statements now that we're going to get into, the building blocks of our command, working our way up. Print statement. We can use what's called a format string. We can just print a simple string, print hello world, or just print a variable. Or we could say print, open parentheses, F, and then a string. And that string becomes a format string. It's parsed by the input argument, right? And there's other ways to do this as well, to where we can actually have, like, you know, calculations inside the string, or we can tell it, you know, print percent or 0x, print a 0 and X in front of the number, right? So we can print out things in a different number base. Instead of base 10, we can print out in base 16, hexadecimal, things like that, using our format. Variable assignment, we assign 5 to variable A, assign 10 to variable B, and then we can say, you know, updated value of A equals the new assignment of value. We've assigned a value of 15, right? So blah, blah, blah. Conditional statements, if. And we saw the else before when we had our try catch block, you know. Well, if has an else, but it also has an else if. If x is bigger than 5, print x is greater than 5. If x is equal to 5, print x is equal to 5. Otherwise, if it's not bigger, it's not equal to, it must be less than, so we print that out, right? So we only get one of the print statements if it's selecting between all the different options in there. Functions, def, add numbers. So we're going to just say def add numbers, x and y are the 2 arguments. We're going to add those 2 numbers together, return the value, right? And so we call add numbers 10 and 20, boom, great. Loops, for loop, while loop. For I in range 1 to 6, print the square of I as I times 2 in a format string. So we'll see the square of 1 is 1, 2 is 4, and so on, right? So it's managing the count for us. While loop, we're responsible for managing it ourselves. We have to initialize. Count equals 1, while count less than or equal to 5. The cube of count is count times 3, or count raised to the power of 3, right? So similar output, just we had to manage things ourselves. This is used for, like, if you've got a flag and you're waiting for it to set. You know, if you're, you know, going to close off the gates when, you know, the 100th person walks into your building, something like that, right? You have to maintain that as a live counter. You can't just be counting it randomly. That wasn't a great example. Classes and objects. Again, a class, by saying class, we end up and give ourselves a namespace, and that namespace is calculator. And everything that's inside that are defined functions, right? And those defined functions are used by that class. Every class has a function called init, underscore init. And this is where we initialize the value of the class to some initial value. So here we say definite self value equals 0. When someone says calc equals calculator, that says create me a new calculator, right? And I don't want to give it a value. So find yourself a default and assign it. So it's we can tell ourselves we have a default value. Any function you can do this, give it a default value for your arguments. So it'll initialize to 0. Then I can define an add method for that object and a subtract method. And they're basically just changing the value of that internal variable. And you notice, of course, this is double underscore init because that is a standard method or function that goes with every single class. And there are other methods that are standard inside Python as well. Importing. We want to import the square root statement from math. Or can you import math module? There is no square root argument in base Python. You have to import math in order to get that because people don't use it. It has a lot of overhead. So basically Python, as you load up the basic Python, you get a stripped down version that runs very quickly. The more capabilities you need, the more libraries you're going to have to import to make your code run slower. So you've got that trade-off. You pull in just the minimum amount of code you need in order for things to run. Exception handling. Again, we got try result equals 10 divided by 0, except print you can't divide by 0. It'll be fine. The return statement. You don't have to return a value from a function. If you don't return a value, it will kind of default to return what it's called not a number or a none value from the function. So it actually returns a value. The value being none indicates it's not a useful value, right? And again, we can return a plus b here. So, and you can have as many return statements in your function as you like. Pass statement does nothing. If you're writing code, I've used this frequently. I've got this code block. I need it to do something, right? I'm going to have a loop in there. I don't know what I'm going to have inside the loop yet as I'm kind of through stuff. So I just drop a pass in there and I'll fill it in later, right? But I can also have code in there where some people will do things like that in order to just have a timer count for a longer time and just spin in that spot of the code. Break and continue. Find range 5 if I equals 3, exit the loop. So it'll print out 0, 1, 2, and stop. If I run it again with a continue statement in there, if I equals 2, continue, so it'll print out 0, 1, skip the 2, 3, and 4. Right? So BizBuzz in Python, maybe, who knows, right? If I%3 equals 1, then print biz and continue, right? Global and non-local statements. And we don't have a non-local example. That's used less. But global, basically, we're saying if I have a function and I define a variable inside that function and there's already a variable with that name, you actually have two different variables. The one variable is inside the function. The other variable is the global variable outside it. So in this case, if I want this function to be able to access the global variable, I just say global and then reference the name of the original function. So I'm telling it, instead of making my own local variable, I'm going to use the one that's out there, global. And just the name is a coincidence. We could call this foobar, whatever, right? But the global keyword is what's important here. So if I modify it internally, then the external one will change. If I didn't have that global statement, I change it, I add 5, and then I print it after the function, it would be back to 10 again. The delete statement is taking something out of a list, throwing it away. Our data types in Python, we've got numbers, integers, float, and complex numbers. I believe complex numbers, you have to import the math module or the complex module to get those. No, those are built in, aren't they? These are built in, complex numbers. Sequences, Boolean values, strings, and none is another sequence, basically empty string. More sequences over here: a list, a tuple, a range, bytes, byte arrays, and sets are kinds of sequences. And then finally, there's the mapping, frozen set, and a dictionary. Where does this go? Set in the mapping or the sequence? You'll figure it out. Yeah. Strings are sequences of characters enclosed in either single or double quotes. Again, these are straight up and down quotes. This is a face looking at us with 2 eyes, you know, whatever, ASCII art. Strings are immutable, meaning they cannot be changed once created. Immutable, from the word mutation, or something changes. Mutable means it can change. Immutable means it's not allowed to change. Text equals hello world, print text, and I can't say text sub 3 equals, you know, P or something, right? I can't change a letter in the string. It's stuck once I change it. If I want to change it, I can make a list of ordered and mutable items in a Python. It can be different data types. It can have a list of characters. It can have a list containing an integer, a string, a floating point, right? I just initialize it using square brackets. It is ordered. As I put things in the list, right, they have a location. That location doesn't change unless I start popping things out of the list or appending things to the back end. Elements can be added, removed, or changed. They're indexed by numbers. If I say my list sub 0, I get a 1. If I say my list sub 1, I get hello. If I say my list sub -1, I get 3.14, because negative numbers for indexes start counting from the back towards the front, right? And they're heterogeneous. A tuple is almost the same thing. It's an ordered collection, but it's immutable. It is also heterogeneous, can store different data types. You declare it using parentheses. So why do we have tuples versus strings? Well, first of all, sometimes you want things to be immutable. You don't want to accidentally change something. You want to create the list of possible states for your state machine, maybe, right? And you don't want someone out there to try to add a new state on the fly. You want to create a new state machine for you. So you'd use a tuple in that case. Lists all sorts of methods for inserting, popping, removing, so on and so forth. In other words, these are things that change the list. Those are not supported in a tuple. Another reason to go reuse tuples is that tuples are more space efficient and more time efficient than lists, because they don't change. They don't have to worry about doing all the checks to see if they've changed, right? So your code is faster if you write it using a tuple. And in most cases, with the level of code we're doing, that doesn't make a whole lot of difference, right? But when you start getting into bigger pieces of code, you want to start doing something where you try to look at efficiency and then figure out what the best way to do it, make it go fast is, right? Dictionaries. Dictionaries unordered and mutable. Each key is unique, used to access the corresponding value. Your keys must be immutable themselves. You can't change the name of a key, right? It's unordered. As of Python 3.7, it actually maintains the insertion order, but you don't go out there and say, give me dictionary sub 0, sub 1, sub 2, right? You go out there and you see the dictionary sub name, dictionary sub age, and dictionary sub city, and so on. Declared using curly braces. From my Perl days, I know that it's called curly braces because it's a fancy list, a fancy array, right? It uses fancy indexes instead of just numbers. So that's why it's a fancy curly brace on there. Comments. These are text that's ignored by the Python interpreter, used to explain, document, or debug the code. Got a small typo here. This is a hashtag or an octothorpe. I still think the octothorpe terminology should have kept on for a lot longer, but anyhow, pound sign is another word for it. But I think if you're a graduate of ADS, you should make sure to call it octothorpes wherever you go. Okay, you're with me on this? No, no, never. You're going to call it hashtags. Yeah, that's fine. This is a single line comment. We just started with a pound sign. I can also put a pound sign in the middle of a line. And so then if I were to like take this away, or if I had x equals tan hashtag assigned value, I think there's probably a missing carriage return here on this, because I think this is supposed to be a line showing how the comment basically starts wherever it is and goes to the end of the line. If you want a multi-line comment, you use triple quotes, triple single quotes, or triple double quotes. This is a multi-line comment. One of the things to point out is if you have a triple line quote after a definition of a function, that's called a docstring. The Python interpreter will actually parse what's inside that as documentation for your function. So you can list out what the expected arguments are, so on and so forth. And if someone's in the right IDE, they just type in the function name, hover their mouse over it, and it will pop up a little tooltip box, tell them what that function is expecting, what it is planning to do, so on and so forth. There's actually Python documentation out there on how to write a good docstring. It's worth looking at. Introduction to Python libraries. They are pre-written code collections that extend Python's functionality, help tasks like data analysis, machine learning, web development. There's where we see where I stole these slides from Perspectives in Data Science, right? NumPy, core library for numerical computing. Arrays, matrices, mathematical functions for arrays. NumPy is NP. Matplotlib is used for creating either static or interactive animated visualizations. You can generate plots, histograms, bar charts, so on and so forth. There was a list from PDS of a good half dozen different libraries that are really useful for data science, but they're not so useful for data storage, right? So I save you a whole 30 seconds by not going through those slides. Python.org is the official documentation for Python, right? And 3.13, yeah, okay. And it's got all sorts of stuff out here, and you can actually just start reading this, and you'll learn Python. Google has a class on how to learn Python. Google also has their own programming language they call Go, which they're trying to convince us to use. That's cool. W3 Schools, Real Python, Free Code Camp. Those are other Python Python resources. And I took out the bit about the other programming languages. That was kind of interesting stuff, but not so relevant for this class. Okay, so let's see, 12:30, 1:30, yeah. Okay, so we're at the end of class now. Any questions about Python programming? Anybody still awake out there? I always joke about how I like to put people to sleep in class. I try not to, but you know, sometimes I just get tired and start talking in a monotone. So today's class, that's the wrong class. Another thing I do want to bring up for your use, we don't need that. This will be posted here this week, is the schedule for the class, the dates. Of course, we did the course overview last week. Today is Python, next lecture is Hamming code, RAID levels, RAID RDP, so on and so forth. So we've got kind of a planned out. If you look at this too close, you'll see that things get a little bit fuzzy in the last half of the semester because we're trying to rearrange things still. But I think we're in a place where we can go ahead and publish this out on Blackboard. So that should be out there, hopefully before the end of today. And the other thing we're going to do is take attendance now. So let's go ahead and hide that. Also stop recording here. Stop recording. There we go.